This online lesson is about cycloalkane ring strain, with which there was a paper packet provided electronically or in hard copy. And so on this construct, there are notes already, and I will add to that. I will provide more notes on top of the notes already provided. This is a forerunner to our lesson, and I figured it's nice to impart to you how different ring sizes are seen within pharmaceuticals and in living cells. All right. So here we have the major ways in which we see three-membered rings, that is to say, cyclopropane rings. The most prominent I would offer is pyrethrins. These are insecticides produced by nature. So good they are that mankind has started to mass produce them in factories. So these are other instances of three-membered rings exist. And here are some four-membered rings. A four-membered ring, anyone asks me off the street, what's the most important four-membered ring? I'd say penicillin. Penicillin is the structure in the lower right, and there's a four-membered ring. Among the members of the ring is a nitrogen atom. We call that a heterocycle. Repeat, heterocycle, because there is a heteroatom as a ring member. That's what happens if you get too much of a sunburn. Your DNA bases will form a four-membered ring, thereabouts. Here we have some instances of five-membered rings. If anyone off the street asked me, what's the most relevant five-membered ring in vivo, I would easily say prostaglandins. So blame prostaglandins for when you have a headache, for when you have a throbbing pain. This is the chemical messenger of pain, prostaglandin, in which there is a five-membered ring. There are others as well, five-membered rings in vivo, that is. Here are some six-membered rings. One page does not do it justice. Strychnine, maybe you can find the six-membered ring in strychnine, the bottom right here. And it's too easy to say that glucose is a six-membered ring, but it is. Why? Because glucose exists as a six-membered ring because six-membered rings have no ring strain. Uh, Six atoms in a ring. These atoms don't even know they're in a ring. They're innocent of the fact. There's zero ring strain, stable ring. Vitamin D is also bearing a six-membered ring. Some seven-membered rings. Some fatty acids, I was not able to obtain a structure, but some fatty acids, carboxylic acid, C double bond O, the same carbon double bond to an oxygen is single bonded to an OH. That same carbon is bonded to a long zigzag, zigzag, zigzag alkyl. At the very end of it is a seven-membered cycloheptane ring, which do have a certain knack to draw those. Uh, so really, nothing's really knocking my socks off here with respect to prostaglandins are the five-membered rings, pyrethrins are the three-membered rings, penicillin is the four-membered ring. So there's really no, clinching fast answer for a seven-membered ring. What's its claim to fame in biology? It's an eight-membered ring. Uh, Again, so there are some representatives, but there's no smart and fast answer as to the world famous eight-membered ring in vivo. There's not much I can put to you there, but I did do a nice run-up. One of these is an anti-cancer drug, paclitaxel, uh, has several chiral carbons in it. And uh, shall we try Nine-membered rings. Poison dart frogs. Their toxin is called, if I pronounce this correctly, Bartracatoxin. Here we have a nine-membered ring. It's another heterocycle with nitrogen and oxygen as part of the nine-membered ring. Plenty of chiral carbons in that, don't you know? And this is a nine-membered ring with two double bonds in it. It's called an ene-diene. There's the ene double bond, the diene, excuse me, an ene-diene, two triple bonds. These 7, 8, 9, 10, 11 membered rings are called medium-sized rings, and so they are not in every phytochemical, but they are in some of them. So there's a flow chart for phytochemicals. Alkaloids are base-like; they would taste bitter on your tongue. Theobromine is in chocolate, so cruel, pure chocolate tastes very bitter, 100% chocolate. Uh, I don't want to make this movie too long, but uh, encyclododecane has actually been used by scientists at the Smithsonian Institute to preserve fossils because this compound here sublimes. It goes from a solid into a gas, so it's very easy to remove the casting. So that's some motivation to start the engine to learn about cycloalkanes and their relative stability. So what we're saying here is that three-membered rings do exist in biology. What do you know? And so off of this worksheet here, which you've been provided or can access electronically, I'll put in some notes and away we go. So, learning objectives. Objective A, I hope you know this already. Contrast alkane to cycloalkane. Cyclo is to ring. So, this is not a cycloalkane. This is not a cycloalkane. It's not closed up in a ring yet. Carbon 1, carbon 2, carbon 3, carbon 4. This is a cycloalkane, cyclobutane. Uh, so, cut and dry. Part B, pick which cycloalkane has the least ring strain, like glucose. A six-membered ring has the least ring strain. As I said before, each of these carbon atoms in cyclohexane doesn't even know it's in a ring. Innocent. They don't even know that they're tied up in a ring. Don't even know it. Uh, Low ring strain. Part C. Pick which cycloalkane has the most ring strain. The most ring strain, for reasons to be discussed, is cyclopropane, far and away. For remembered rings, you see them in perithrins, or they do exist in vivo. But these three membered rings have the most ring strain. They have the most pent-up energy. If you were to take a match, strike it, burn, cyclopropane, three-membered ring, triangle, burn it. And if you take another match and burn propane, you would see extra heat emanated from cyclopropane because that extra strain, that extra pent-up energy, if you burn a molecule, will produce more heat. The heat content of a molecule is increased for a ring compared to a straight chain. More on that in a bit. Part D. Understand the actual shapes of cycloalkanes in nature. They are not flat polygons, but they are butterfly conformation, envelope conformation, and chair conformation. Don't have to take my word for it. I will take you now to mole view. Okay, take a look for yourself. I drew these molecules with my mouse. On the left side is polygons. And look what we are turning these up as. These are presenting as, is this flat? Don't think so. That is not flat. That is not a flat ring. I drew it as flat. This is cyclobutane. It's not flat. I drew this as cyclopentane, pentagon. It doesn't look flat to me over here, huh? It doesn't look horizontal flat. Uh-uh. I drew this as a cyclodecane, the fine art of counting. Cyclodecane. This is definitely not flat. Uh, The only one that's flat, is cyclopropane. That's the only one that happens to be flat. Don't you agree? Cyclopropane is flat. So any ring besides cyclopropane will be not flat. Cyclopropane flat. Any other ring is not flat. So the rings did this spontaneously. If you were to construct a plastic model of cyclohexane and try to make it be flat, it would on its own accord become not flat. I just made it be flat. Now it's not flat anymore. The molecule did that by itself. I will try to make this cyclododecane be flat. Not doing too good, am I? On the table. I have no such luck of making this flat. I will cyclopentane, make it be flat. It's flat. Leave it long enough. I see right now that this vertex is starting to creep up a bit. Against gravity? Yeah, against gravity. These, look at this one right here. It's starting to creep up a bit. So these ring carbons prefer not to be flat. Why? Wonder why. Talking about that very soon. So we understood that according to MolView, the drawing program, and according to the models I held up with my hands, that these ring carbons spontaneously become not flat for everything except cyclopropane. Three-membered ring flat, three-membered ring flat. Everything else not flat spontaneously. Point F, we'll look at this soon. I'll show you soon. A graph on the y-axis will be pent-up energy or strain or extra heat content. If you burn this, you burn that, you get more heat with that because it's a ring. Strain. Extra heat content on the y-axis against ring size. Three-membered ring, four-membered ring, five-membered ring on the x-axis. So we'll see that plot soon. Here's a definition for you. Ring strain, also called Baeyer strain after Adolf Baeyer, is equal to three parameters. They are, in any particular order, what's called angle strain. Add that to a ring's torsional strain. Add that to a ring's transannular strain. So that's ring strain. The formula of ring strain is equal to ring strain equal to pent up energy in a ring is equal to angle strain. What's that? Plus torsional strain. What's that? Plus transannular strain. What's that? Definitions upcoming. Define strain. Uh, Strain, as I said, is this pent up energy, this unexpected, I repeat that, unexpected pent up energy. Uh, for instance, when you strain your back, that's not a good thing, is it? So strain is pent up energy, energy of uncomfortableness, uncomfortable, too much, extra pent up energy, strain. Is it good for a molecule to have strain? Is it good for you to strain your back? No, and no. We're on I now. To draw cycloalkane conformations with good line angle formula. We'll see if this movie can capture that. That's generally not only the emphasis of this movie, perhaps. J, to present molecular models by camera of cycloalkane standing up, also under mole view. Mole view does a better job, gives you a better background, and so it's better than me doing. So I've decided to go the mole view route more so. And K, present the molecule cholesterol as a case study in ring strain. So if you take a look at a molecule of cholesterol, you'll see that there are three, count them, one, two, three, six-membered rings, and one singular five-membered ring. Steroids are instructing us that six-membered rings are very stable, and the second place stability of a ring is a five-membered ring. That's the next best stable. Cyclohexane, six-membered rings, very stable. As I said, these atoms in cyclohexane don't even know they're in a ring. Five-membered rings are the next most stable. Another definition for you. Steric. Please note that the word steric ends with the letter C. Steric is to bulk, and bulk is to clash, clash, fighting over the same space. Steric is to bulk, steric bulk. Oftentimes they're said back to back, steric bulk, hyphenated or something like that. Steric bulk is to clash, is to crowded. Steric is to crowded. Here are some inequalities for you. In terms of sterics, what takes up more space? Does an ethyl group take up more space than a methyl group? Yes. So therefore, ethyl is more steric than methyl. That's why we learn these groups, right? Hopefully you can envision them in your mind. What takes up more space? Ethyl or N-propyl? Of course, N-propyl. N-propyl is more steric. And so, as you'll see here, if something is branched, it becomes that much more steric, okay? So branching tends to increase stericness. So something's branched. That's the idea here. So isopropyl, branched as it is more steric than N-propyl. Example, T-butyl, hyperbranched, is more steric than N-butyl. T-butyl is like a big boat anchor. It's going to take up a lot of space, whereas N-butyl is more straight chain. It doesn't take up as much space because it's a longer and more of a rectangle shape. T-butyl is also more steric, takes up more block space than isobutyl. Uh, Definitions for B, strain is pent up energy. Strain. When you think strain, think pent up energy or think strain your back. So the strain is not desired. Molecules desire to do resonance, yeah, but they do not desire to have strain. Okay. So torsional strain, and it gets down to it because remember, ring strain, ring strain has three components to it. Ring strain, the total pent-up energy in a ring is a little bit of this, a little bit of that, a little bit of that. Torsional strain, add to angle strain, add to transannular strain. So torsional strain, may I explain? So torsional strain, This definition, whereas steric is the bulk, this definition of torsional strain isn't really that helpful. Okay, it's kind of an anachronism of a word. It's an ancient word. It's kind of lost its meaning. We're stuck with it, so we'll have to do with that what we can. So torsional strain, this unfortunate name for this type of strain, where we're living with it. Torsional strain is due to eclipsed bonds. What's so bad about that? Well, as you know, a bond is composed of how many electrons? Two electrons. Two electrons in a bond. And so if we have bonds which are eclipsed, torsional strain, if we have bonds that are eclipsed, torsional strain, I just eclipsed them. Now you see it. See where my green cursor is, I hope. I can make it eclipsed just by using my mouse a bit. You can't see that anymore, can you? Sorry, I did it. You can't see that anymore. Well, what's so bad about this? Well, don't you know there are two electrons in this tracing of a bond and two electrons in that tracing of a bond? Electrons have what charge? Negative. Will a negative charge repel a negative charge? Yeah. A negative charge will repel a negative charge. So we have in one molecule, we have eclipse bonds, and the electrons in the bonds are repelling each other. The molecule is grinding and tearing itself apart because these bonds are eclipsed. Eclipse bonds, dot, 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 electrons repulsions. Eclipse bonds, electron repulsions. Torsional strain, eclipse bonds, electron repulsions. Not stable. I'll rephrase my definition for you. Torsional strain. Sometimes the less words in a definition, the better. Torsional strain, eclipse bonds. We're invoking eclipse bonds. Electron repulsion inside a molecule. Dot, dot, dot. Molecule intra, that means inside one molecule. Repulsion. That's not too stable. Like if you have inside a holistic molecule, if you have repulsion between this bond and that bond, that's why would that be stable? So it's not. So torsional strain, eclipse bonds, electron repulsion inside a molecule. That's probably as boiled down and distilled as I can make it for you. Okay. So angle strain. As you know from Vesper, tetrahedral carbons and rings should have a bond angle of 109 degrees. I don't think we're seeing that with cyclopropane, 60 degrees. I don't think we're seeing that with cyclobutane, 90 degrees. No, 88 degrees. Cyclobutane has angles, carbon-carbon bond angles of not 90, looks like a square, but it's not. 88, not 90. Why does it do 88? Let me explain. So we're talking about angle strain. So angle strain, what comes about with angle strain is the fact that if you're not getting good uh, just gonna show this now. If you're forcing lobes, which should be bonding at 109 degrees, to bond at 60 degrees, sorry, the orbitals are not going to meet head on. They're not going to meet head on. They're going to meet at an angle. And if they meet at an angle, then the bonds will not be as strong. There's not as much orbital overlap. The more orbital overlap, the stronger the bond. Ta-da. But if we are scheduled to have bond angles of 109 degrees, and this cyclopropane has a bond angle of 60 degrees, the orbitals will not meet head on. They'll meet at an angle. They'll meet at an angle. That's not good. You got weaker bonds, more pent-up energy. back to the models. No doubt, right? 60 degrees. That cut there, 60 degrees, 60 degrees. Can you find torsion? Torsion is eclipse bonds. There, I did it. Do torsion. Bonds eclipsed. What just happened? Electron repulsion for the carbon hydrogen bonds. Add on to that, but add right on top of that, angle strain, 60 degrees. That should be 109. Wider than 90 degrees. Wider than 90 degrees. This is 60. What happens with angle strain? The orbitals. What about them? Orbital overlap is worse. What about it? Weaker bonds. But strangely enough, they still exist in pyrethrin, the three-membered ring. So, but maybe now you're seeing why cyclopropane is more expensive to purchase. Here's cyclobutane. I drew it as a square. It's a square. Looks like 90 degrees, but it isn't. How come? If you read the textbook, your textbook would say cyclobutane, I think the verb is compensates. Okay? So cyclobutane will take on itself extra ring strain. Okay. It'll suffer from 90 to 88. Oh, that's too bad. Worst orbital overlap. But now we don't have torsional strain. I can't eclipse these. Easy peasy over here. I can easily eclipse gray, white carbon hydrogen bonds there. Easily done. Over here, cyclobutane, and going from 90 to 88 degrees, now we don't have any more torsion. Oh, cyclobutane, how clever. How clever cyclobutane. And so it must be that the amount of torsional strain being saved and averted is so much more impressive than the amount of angle strain being suffered. And that's the case. Can I find and show you eclipse bonds in cyclopentane? Not quite. They are almost eclipsed. Take a look at this, will you? Take a look at this, will you? Where the green cursor is. They're not fully eclipsed. They're partly there. So that's why cyclopentane is the second most stable ring size. Not much strain. The angles are getting better. Closer to 109 degrees, right? The angles are getting better. And there's no torsion. Poor cyclopropane. 60-degree bond angles, poor orbital overlap, meaning a glancing rather than head-on, a glancing orbital overlap. Cyclobutane's a little bit better. Wider bond angles, 88 degrees. How come not 90? Because it's doing a great job at getting this hydrogen. So you can see the entire circle, can't you? These are not too eclipsed, not too bad. It's a little closer call here, cyclopentane, but it does have a uh, uh, less, next to nothing ring strain. And how about this thing here? Are these eclipsed? Oh no, not even. Take a look how far away these are. I just made this gray atom and that gray atom eclipsed. You cannot see the gray atom in the back now, can you? Uh-uh. Look how far apart they are. So with the large size rings, they don't have a problem too much, too much with angle strain. Actually, when it comes down to it, their angles are too wide, 116 degrees, 116 instead of 109. So not too bad. Torsional strain? Not at all. Not at all. Nothing's eclipsed. What's the problem with what is the issue with a large size ring? How come bigger isn't better? Because with a large size ring, these hydrogens kind of get in each other's way. This is my space. Get at. No, this is my space. You get out. So these hydrogens in the middle of the ring are clashing. What was the word for that? Beginning with the letter S. Sterics are clashing over the space. So that's the problem with the large size rings, everybody. The larger size rings, cyclononanes, cyclododecane, angle strain, check. Torsional strain, just fine. No eclipse bond angles. Transanular strain, uh-oh. I can do it with my models a lot better. You hear that? Clank, 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 clank. Get away. This is my space. No, it's my space. These hydrogens are on opposite sides of the ring. Look, I just spread them apart. Do you believe it? Can you believe that? Look how far apart they should be. They should be far apart. But I can do this. I can do that. Clank, clank, clank. Transannular strain. Transgender strain. It's attributed to larger cycloalkanes, in particular where a hydrogen atom at ring carbon number 1 in cyclododecane clashes over the same space as a hydrogen atom at ring for ring carbon atom 7. Trans in transannular. Trans means across, like transatlantic flight. Trans is across the ring. These hydrogens should be across the ring, trans. They should be out of each other's way. These hydrogens. Are they out of each other's way? The ring is floppy enough that they could be bothering each other, these hydrogens. So transannular. So transannular really is applying to larger cycloalkanes. Cyclopentane, no transannular strain. Cyclopropane, no transannular strain. So transannular strain is really kind of reserved for C9 and upwards. Cyclononane, cyclodecane on up. Transannular strain. That is a component of ring strain as well as angle strain. Angle strain. Angles are pinched. So what? Orbitals don't meet head on. So what? Weaker bonds. Okay. Torsional strain. So what? Bonds are eclipsed. So what? Electron repulsions. A bond is made to electrons. This bond is made to electrons. That bond is made to electrons. Repel. So what? The molecule is tearing itself apart from the inside. It's intramolecular repulsion. Doesn't sound too good for molecule stability, does it? So we see angle strain. It does exist, as I said in passing, for larger sized rings too, where the angle is too wide, 116 degrees in cyclododecane, for instance. But the more troublesome aspect of uh, angle strain is the smaller rings, cyclopropane, cyclobutane. So I believe I did a good enough job with the limitations of an electronic lesson to explain these strains. Question becomes, by the way, a steroid molecule, when you're looking at it, six-membered rings, five-membered ring, very instructive. So the question could be, if you were given a molecule, a plastic molecule of cyclopropane, and you were tutoring someone, making some money, by the way, about ring strain, how would you explain to your uh, audience that this cyclopropane has torsional strain? What would you point to? What would you point to explain cyclopropane has torsional strain? Question number one. How could you hold a molecule of cyclopropane in your hand and explain the premise of torsion strain to someone else? What would you point to on the molecular model? The same applies to transaminase strain and cyclododecane. The same applies to angle strain and cyclobutane. What I would point to, this is a model. Think these bonds are straight? Doesn't look it. That's angle strain with the plastic pieces available on Amazon. Molecular model kits. Can't believe how this is angle strain. Look at this. Believe this? So what I would point to with respect to torsional strain, not angle strain, is the fact that I'll tap it. Pardon me. I am doing my best. So these bonds have two electrons in them. These bonds are repelling each other. The electrons are repelling. It was bad enough you got a kinked, not straight bond. Then you have this torsional strain. Man, that's cyclopropane. I think I put that very vividly for you. Okay, so that could be uh, a question on a test. Okay. This is just the next slide is just some kind of reiterations of what you learned already, some pictorials, because the previous slide didn't have many pictorials on it, if any. The ones I drew, I guess, the notes you took. Rotate and view to the right. So once again, ring strain is equal to, you got this, angle strain plus torsional strain plus transangular strain in any particular order. Angle strain, the angles are too narrow. Angle strain, poor orbital overlap, even in cyclobutane. Yep, right. How's about torsional strain? These portals go as columns. So if I can set this apart here. So angle strain, I mentioned that more than once. Uh, and torsional strain, just talked about that. Torsional strain is due to eclipse bonds. It's kind of an unfortunate definition that we're stuck with. Torsional strain. I wish they would call it eclipse strain. That would be good for you, good for me, but we're all stuck with it. So someone else born before you and I named it torsional strain, and we're stuck with it. Transannular. And so, by the way, everybody, the symbol for sterics in organic chemistry is two interpenetrating parentheses, parenthesis, parenthesis. So that's what you're seeing here. These parentheses, which are interpenetrating, however else you put it, clashing, steric clash, uh, transannular sterics, transannular sterics. Steric is to clash. Now, I grant you, a hydrogen is much smaller than a terbutyl, but they're still clashing. Sterics occur within the ring. This hydrogen is on carbon number one. What's it doing so close to the hydrogen on carbon number five? The ring is too floppy. And we do see angle strain. As I said earlier, the angles are too wide. What's the problem? Well, it's only that the orbitals will not meet head on. They'll meet at a glancing blow. Okay. Orbitals not efficiently overlapping, weaker bonds. Here's, oh, how awful. As an organic chemist, seeing orbitals looking like this bothers me. These orbitals should be meeting head on, like we saw in chapter one. Come on, that's what's supposed to do. This, oh, for Pete's sake. So I'll run through this with you. So I'm not going to define those, but I will fill this out for you. So does cyclopropane have Torsional strain. You better believe it. Does it have angle strain? Yes. Does it have transgender strain? Nah. Cyclobutane, torsional strain? Yes. Not as bad, but yes. Uh, just a bit of it. They're not as eclipsed. Angle strain? Yes, but not as bad. Transgender strain, we said that's reserved for larger rings. No. How about cyclopentane? Torsional strain? No. It's doing pretty good. Angle strain? A bit. Just a bit. Transgender strain? Nah. Cyclohexane? Nah. 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 As I said, these atoms, these six atoms in cyclohexane, don't even know they're in a ring. If you burn, if you combust 1 mole of cyclohexane, and if you combust over here 1 mole of hexane, they will each release the same amount of heat. That must have been that the ring doesn't have any strain in it. It must have been. Tozer strain, I don't know, not too bad. Angle strain, a bit. Angles are too wide. Transgender strain, not yet. Cyclooctane, torsion strain, no, no, a bit. Angles are too wide. Angle strain, not quite yet. Uh-uh. Torsion strain, no, no, not a problem at all. Angle strain, yeah, a bit too wide. Transgender strain, don't do it. Sorry, gotta, yes. And this pattern will a bit more. And yes. Oh boy, another one. Uh nope. No bond eclipsing. Angles are too wide. Angle strain. Yes. So this can be presented as graphical, but let's zoom out for a minute for your note's sake. That's what we have on report. So we remember pyrethrin, a three-membered ring. We remember penicillin, a four-membered ring. Did you know that penicillin was a four-membered ring? We remember prostaglandin, the chemical of pain, a five-membered ring. Glucose, a six-membered ring. No wonder glucose is the uh, major metabolite in the body. It's a six-membered ring. Same stability as that of a chain. No wonder we don't see eight-membered rings as sugars in biochemistry. Small wonder compared to six-membered rings. Here we have, as we start to wind this down a bit, thanks for your attention. I'm making it as interesting as possible. You can be the judge of that. So this graph here, whenever you yourself are presenting graphs in front of, standing up in front of others sitting down, you should announce the axes. It makes you look more professional. So on the y-axis is you see here the amount of strain, instability of heat energy in kilojoules per mole. And on the x-axis is ring size. So this is 5 kilojoules per mole extra heat released, 10 kilojoules per mole extra heat released, burning a ring compared to a chain, 15 extra kilojoules a mole of heat released, burning a ring compared to a chain, 20 unexpected extra bonus. Ooh, that's hot. Kilojoules per mole of heat release compared to burning a straight chain. And here we have a two-membered ring. There are none. A three-membered ring, a four-membered ring, five-membered ring. There's a dot there. Five-membered ring, six-membered ring. And it's an interesting shape of a graph. It is it's it's two what I could put to you is that it's kind of like two bell curves, Gaussians, where the first Gaussian has a larger amplitude than the second Gaussian. How about that? If someone asked me to describe this shape, that's what I'd say. Well, you're not seeing this because there's no rings. So it's, yeah, so of course there's no ring size over here. So yeah, I feel like John Madden. So, uh, and the notes I put up here is uh, not to be forgotten. Don't want to forget this. So when you're looking at this graph, it's not to bring it home. They could say how much extra. Unexpected heat energy in joules is obtained if you burn a cycloalkane compared to burning a straight chain alkane. And by the way, the data you're looking at normalizes the number of carbon hydrogen bonds for comparison of ring to chain. In other words, C3H6, cyclopropane only has six hydrogens. Propane has eight hydrogens, the end caps, the end points. They have one more hydrogen apiece. So this is all normalized, so it's even Steven. And so here are some torsional strain and angle strain attribute to why these are so bad. Torsional strain, what comes to mind? It begins with the letter E, eclipse bonds, right? Uh, and when we come out here, these larger size rings, we're chalking that up to angle strain. What happens with angle strain? The orbitals blank do not meet head on. What's transannular strain? Trans means blank, begins with letter A, across. Transannular strain. So that's why these are creeping up, but then it's settled back. So it appears that cyclononane, which I did show you a few structures of beforehand in vivo, these appear to be the most unstable ring of a larger size beyond that of cyclobutane. And so cyclopropane, most unstable. Congratulations. Thanks for nothing. Cyclobutane, next most unstable. Second place unstable. Third place in terms of instability is cyclononane. And I can reconcile the fact that the cost for purchase on a budget at an academic or federal or municipal or state or private place of business, if they're going to purchase these cycloalkanes, it will just go along with what this chart said with respect to stability and instability. The more unstable the ring, the higher the cost for that concern to purchase. So three-membered rings, you are spending $22 per gram of material to purchase a three-membered ring. So six-membered rings, it holds true. These are where's the data for 9 and 10? Something they don't even sell those. Aldrich does not sell cyclononane. Tell you something? I was surprised that Aldrich does not sell cyclobutane. I didn't know that, but they don't. And so I'm driving to the end here. Made it as interesting as possible talking about in vivo rings. And so I'm pretty happy with this lesson. So I hope you can answer this true and false question before looking at the answer it is on there. True or false, all cycloalkanes exist. Oh, this is awful. This is easy. All cycloalkanes exist as flat polygonal rings in nature. False. Cyclopropane does, grant you, you saw that, but others do not. Why? Because we can minimize torsional strain. That's what cyclobutane did. Crafty cyclobutane. It went from 90 degrees to 88 degrees. In so doing, it removed itself from eclipse bonds. Cyclobutane is pretty smart if we had to personify it. So I believe I'm gonna just end it here after putting these comments in here. There, see, look, 88 degrees, right? We talked about that. So I would supply to you that the shape of cyclobutane butterfly shape. It has a certain shape. Mind you, molecules are always in motion unless you are living at 0 degrees Kelvin, even space, outer space at a temperature of 4 degrees Kelvin. So as long as there is temperature, molecules are moving. That's why they called it the butterfly conformation, because it's jiggling like a butterfly, if you will. And cyclopentane is called the envelope conformation. You can consider it like there's a wave at a basketball game. college or pro going across the stadium. Everyone does the wave. They sit up, they shout, put their hands over their head and sit down and enjoy the wave, see how long it goes, see who starts it, see who lets it down. So cyclopentane is the envelope conformation, the envelope shape. Conformation. Form is the shape. Conformation. We're talking about conformations. So the word conformation, if you look at it with good spelling, in it is the word form. In this long contorted word, conformation is form, and form is the shape. What shape does cyclobutane exist? As butterfly. And I would add, true or false, molecules are in motion at room temperature. Oh, true. They are vibrating, somersaulting, if that's how you spell that, translating, that is moving X, Y along the Z-axis, along the Y-axis with velocity, translating along an axis, they're rotating, and you name it, they're doing it. Molecules are not rocks. Molecules are not rocks. They move. You think the plasma membrane in your cells is a static rock? It is not. It's jiggling, it's jostling, it's moving. Molecules are in motion. They're moving. This is the envelope conformation. Envelope shape. That's not what I came up with. That's a textbook term. Here we have there's a separate lesson about this, the chair conformation, lawn chair, I guess. But they call it the chair conformation, chair shape. This shape here is the boat shape, boat conformation. And here we have another lawn chair shape conformation. By assuming chair conformations, cyclohexane can remove any and all torsional strain. Torsional strain, what comes to mind? Begins with the letter E, eclipse bonds. So you take a flat polygon, a hexagon, a flat boring hexagon, bend one carbon vertex down, bend one carbon vertex up, and you have a chair conformation. It was boring flat before. Look how boring. Boring and flat, flat and boring. And you bend one carbon and the other carbon, and you can get a bent shape, cyclohexane. And I would assume that, and I will go with it, that cyclooctane duos has no butterfly or envelope or chair, has no nickname conformation because it's too flexible. It's too flexible. There are too many shapes it can assume, too numerous to mention, too numerous to mention. The more atoms, the more degrees of freedom, the more shapes. Transannular sterics, can you draw it? If you were challenged to draw transannular sterics, what would you do? What was the symbol for sterics? Two interpenetrating parentheses, right? Which had more sterics, methyl or N-propyl? Steric is to clash, bigger. N-propyl is bigger than methyl. N-propyl has more sterics. What has more sterics? S-butyl or N-butyl? S-butyl is branched, therefore S-butyl has more sterics. So you and I did the best we could with this electronic lesson. We'll close it down. Thank you for listening, and hope you got something out of it. Let me know, follow up in case you need something presented in a different way. Signing off. Thanks.